You may remember from algebra that some functions have what are called inverses. Now, they don't all have inverses, and in fact, this one, as it's written, does not. I'm going to change the domain a little bit here, restrict the domain so that we can talk about the inverse of this function. I'm going to say that x has to be greater than or equal to 0. And I can find the inverse of that function by reversing the roles of x and y and then solving for y. So y equals the square root of x is the inverse of x squared, the inverse of the function y equals x squared. And a little bit farther along in algebra, we start using this function notation. So if I have f of x equals x squared, then when I'm done, I can write this, the inverse function in function notation as well. But I'm going to use this sort of superscript -1, the square root of x. So f inverse of x, which is this function right here, is the inverse of the function f of x. And what an inverse is, what it does essentially, is that whatever f does to x, in this case it squares it, f inverse undoes. Here we're unsquaring, right? And I could give you lots more examples, but that's not the point here. The point really is just to remind you what an inverse is and what it does, because now we're going to talk about what it means to be the inverse of a matrix. We can also talk about, before we get to that, we can also talk about what it means for a number like 3 to have an inverse. 3's inverse is 3 to the -1, or 1/3. It should probably be pointed out that what we mean by a number having an inverse is that it has a multiplicative inverse. There's also an additive inverse, but we're not talking about that here. We're specifically talking about a multiplicative inverse. And what that means is that 3 times 3 inverse is 1. 3 times 1/3 is 1. And that's what we're going to be looking at with our matrices as well. Sort of, but that's the general idea. That's what a matrix, or sorry, that's what an inverse does. So what does it mean to be the inverse of a matrix? Well, if I have a matrix A, there we go. If I multiply it by its inverse, then I should get 1, or the equivalent of 1 in matrix land. And the equivalent of 1 in matrix land is the identity matrix. Because remember that what we said earlier about matrix I was that if you took A and you multiplied it by I, you would just get you would just get A back, right? So this is what it means to be an inverse matrix. The inverse of matrix A, when you multiply A by its inverse, gives you I. Okay, and it turns out, because of the properties of inverses and identity matrices, that the inverse of A multiplied by A is also I. And that's important because remember, multiplication of inverses is not commutative, generally speaking. But when we're talking specifically about A and its inverse, or any matrix and its inverse, multiplication in either order gives you the identity matrix. Now, your matrices here have to be, A has to be a square matrix. Only square matrices can have an inverse. But it's also true that sometimes when you multiply together two matrices, two non-square matrices, you might get I. So it's sometimes true that A times B equals I, but that does not necessarily mean that B is the inverse of A. Okay, so just something to keep in mind. Not only that, but just because A is a square matrix doesn't mean that it will have an inverse. Not every function has an inverse, and not every matrix has an inverse. We can check to see whether two matrices are inverses of each other by checking that the multiplication of the first matrix with the second matrix, and that the second multiplication of the second matrix with the first matrix both result in the identity matrix. So let's do that here. Let's call this A and this B. And let's check to see that AB equals the identity matrix and that BA equals the identity matrix. And if they both do, then we'll know that B is the inverse of A. So let's check that for AB, and then we'll go back and do it for BA. AB is going to be -3 times 3, which is 9, plus -2 times -5, which is 10. So I'm going to have -9 plus 10 as my first row, first column entry for A times B. Then I'll have -3 times 2, which is -6, plus -2 times -3, which is +6. -6 plus 6. Then I'll do the same thing for row 2. -5 times 3 is 15, plus 3 times -5 is -15. And lastly, 5 times 2 is 10, plus 3 times -3 is -9, 10 minus 9. And that, of course, when I simplify it, is 1, 0, 0, 1. And that's the identity matrix. So AB is the identity matrix. But that's not quite enough. I also have to check it for BA. Let's do that next. I think I'll try to squeeze that in over here. BA actually, you know what I think I'm going to do is rewrite it, because it's really hard to do this, at least it is for me, when the matrices are in the wrong order. So BA is 3, 2, -5, -3 times -3, -2, 5, and 3. And that matrix multiplication gives me 3 times -3 is -9, plus 2 times 5, which is 10. It's looking good so far. That's going to be 1. Then I'll have 3 times -2, which is -6, and 2 times 3, which is +6. -6 plus 6. Then the second row gives me -5 plus -5 times -3 is +15, plus -5 times -3 plus -3 times +5. That's +15. That's -15. And lastly, -5 times -2 is 10. -3 times 3 is -9. And 10 minus 9. And that is also 1, 0, 0, 1, which is the identity matrix. So I can say that AB, I'll write it down here, AB is equal to BA, and they're both equal to I. And that means that B is the inverse of A. Now, all I've done here is confirm that two matrices that I were given, A and B, were in fact inverses of one another. I haven't found the inverse yet. That's going to be the topic of our next video. But in order for a matrix to be an inverse, we have to understand what it means to be an inverse. And what that means is that when you multiply that matrix, multiply a matrix with its inverse, the result will be the identity matrix.